So we know that a random variable x is simply a function from the sample space onto the real numbers. We say that the random variable is discrete if the range of x is finite or countably infinite. There is another important class of random variables called the continuous random variables, and those are the topic of this lecture. Discrete random variables have an associated probability mass function, while continuous random variables will have an associate probability density function, and they will be defined differently. We defined the discrete random variable from its range. Unfortunately, we cannot do the same thing with the continuous random variable. However, it is typically the case that the range of a continuous random variable is an interval. So the range of a continuous random variable could be something like 0 to 1, meaning that every real number between 0 and 1 is a possible outcome for this random variable. The interval may be unbounded, so we could have a continuous random variable with a range 0 to infinity, or even a range minus infinity to infinity. Here are some examples of continuous random variables. The length of a telephone call in seconds, for example, where any real number greater than or equal to 0 is a possible outcome. A second example would be the exact volume of water in a bottle. So moving on to the definition of a continuous random variable, we say that x is continuous if there is a function f, which we will call the probability density function, such that any probability, such as the probability that the random variable will take a value greater than or equal to a and less than or equal to b, can be evaluated by figuring out the integral of f of x from a to b. If there exists such a function f, such that all probabilities can be found by integrating this function, then we say that x is a continuous random variable. The function f is called the probability density function, abbreviated to PDF for the random variable x. The probability density function in turn is determined by the experiment, the sample space, the probability measure, and the exact definition of the random variable. However, in probability theory, it's way more common to specify the probability density function. And once we know the PDF of the random variable x, we can calculate probabilities simply by evaluating integrals. So here is a simple example. Let's say that the range of my random variable x is between 0 and 1. Let's say that my probability density function looks something like this. If I want to evaluate the probability that x is between 0.5 and 1, all I need to do is to simply calculate this integral. So this area here, this area is the same as this probability. So it's the integral from 0.5 to 1 f of x dx, where this is my PDF. We always make the domain of the PDF equal to the collection of the real numbers. And we simply set f of x equal to 0 if x is not in the range of x. So in the example above, if the range of x was 0 to 1, then f of x is really 0 over here and over here. It jumps to whatever. A continuous random variable always has an infinite precision. Since continuous random variables have an infinite precision, the probability that x will take a particular value small x must be 0. When we say the probability that x is equal to 0.5, for example, we do not mean the probability that x is approximately 0.5. We mean the probability that x is 0.5 with an infinite number of zeros following that 0.5. So that needs to be equal to 0. Since the probability of taking on a specific value is 0, the consequence of evaluating probabilities of inequalities will be as follows. So this probability that x is greater than or equal to a, less than or equal to b, is the probability that you end up in this interval, including a and b, while this probability is the probability that you end up in the open interval a through b, where a and b are not included. Well, these probabilities must be the same if x is a continuous random variable. We can always write this probability as the probability that x is strictly in between a and b, plus the probability that x is a, plus the probability that x is b. Since this is 0 and this is 0, these probabilities must be the same. You will also get the same result if you have a strict inequality on one side and a non-strict on the other side. So for continuous random variables, it doesn't make any difference if you used less than sign or less than or equal to sign. For any continuous random variable x, its probability density function must satisfy one condition. And that is, when you integrate the probability density function over all real numbers, then this must be equal to 1. The integral over all real numbers is equal to the probability that x will take a value between minus infinity and infinity, and that must be 1. X will always take a value. If the range of x turns out to be something different than minus infinity to infinity, for example, if I have a range of my random variable x which is just from a to b, well, in that case it's the integral from a to b f of x dx that must be 1. This will not contradict the property, because we can always write the integral from minus infinity to infinity f of x dx as minus infinity to a of f of x dx plus a to b f of x dx plus b to infinity f of x dx. If the range of my random variable is from a to b, then f of x is 0 outside that interval. So that means that it's 0 between minus infinity and a, and this must be 0, same reason this must be 0. So the integral from minus infinity to infinity will become equal to the integral where we only integrate over the range of x.